What's up? Thought I had heard a message, or thought I heard you call and then hang up or something. There's nothing there. ah. What do you mean? I mean, show me the difference, I guess. I guess as long as you don't switch windows. Oh, I can. I do not see a mouse pointer anywhere. On Logisim, I think it does though. If you go back to Logisim just to verify that. Yes, I see a hand. It has their own pointer.
We're live now? Yeah. Yeah, no. Yeah, because Photoshop it has like its own special pointer. It's like the brush shape pointer. So,
mm-hmm.
yeah, okay. That somehow fucks with Skype. But oh man, now I want to ask the people in anyone watching in chat, can you see the mouse pointer on this?
I can see it in the YouTube video on the stream.
Okay, you can see it on the stream. Okay, that's good.
Yeah.
All right. So the people watching, it's just you. Okay, you don't count. You don't.
Just don't ask me anything when you go to Photoshop.
Yeah, like I point something. What do you think this is? Give me your expert opinion.
Looks like a giant.
All right. So how you doing, Papa? What's new? What's up? Not much.
Nothing.
All right, that's good. same here. I've been spending.
So yeah, I was gonna say you've been a bad boy, I hear.
I've been spending so much time like just fucking around with this with the CPU that I've been working on, and maybe time that is not actually my own time from a employment standpoint. But anyways, I want to get into that too far.
Right.
You'll never know who's watching. All right, so let's get her going. Let's do this thing. What I want to do today. I think last time I said we're going to do State Machine, but actually I lied to you. I'm not going to do State Machine today. What we're going to do is we're going to make some RAM for our computer, first of all. We're going to figure out how to do that. And we're going to look at some other junk like multiplexers and decoders that we're going to need. And we're going to get the data unit all set up nice so that when we get into the control unit, we don't like have to halfway through have to reroute all the wires, and that'll just be a nightmare. So we want to get it all squared up before we dig into the control unit. Does that sound good, Papa?
Sounds good. So is RAM going to work similar to your registers? Or?
Yeah, basically, all we're gonna do is we're gonna put a bunch of registers in there, and we're gonna have them addressable by some address lines. So we'll be able to select which register you want to read or write from. Write
Okay.
to. Yeah. So what we'll do is, well, let me just let me think here. Add circuit. So we'll call this one RAM. And we're going to add some memory. Well, the thing about RAM is, okay, so you're gonna have like registers, and every register is going to be a memory location basically, and you're gonna need a way of selecting. Let me think here. Let's go to Photoshop. You're gonna need a way. What happened to my layers? Oh God, never mind. Okay, sorry about that. All my stuff disappeared in Photoshop. It was weird. You guys can't see it. It's fine. No, that's not good. You get the weird checkered background there.
That's a transparent layer.
Yeah, that's a transparent layer because everything merged the background for some reason. I have no idea. So what I need is I need Photoshop to stop flipping out on me here. What if I load? What if I go open? Oh, weird pictures showed up there. Just ignore that.
Quick rewind and pause.
No, don't do it. Here we go. Okay, CPU stream. Oh, okay, I opened the wrong one. Yeah, there we go. Okay, now I've got two things open. Now if I close this one, and yeah, no, don't save changes to that. Please just... Oh God, it's happening all over again. Okay, so like I was saying, wait, Papa, can you see the stream? Is this showing up?
I haven't looked at the stream, but it's on.
Let me just look at OBS. No,
No,
it looks okay.
Okay,
looks
there
good.
it goes.
All right. Okay, so like I was saying, you're gonna have a bunch of RAM modules or registers, registers. And what you're going to need is you're going to have like an input. So let's say you've got 4 memory locations. So for binary addresses, thanks, Robert. What you do is you got 2 lines that gives you, 4 combinations of inputs there. And what you want is you want something that'll decode that into single selection lines for each of the registers. So to make our RAM module, we're going to need a decoder, a binary decoder, in order to decode our addresses into select lines for our registers. So that's what I am going to make first, is binary decoder. Basically, the main philosophy of this series, and bind deck, there we go, is we're not going to use any components unless we've already proven that we can build them ourselves. And once we do that, then we're going to use the ones built into the library because they're a lot faster. There's a lot less simulation going on. So binary decoder, all we need is we need some AND gates. We need one AND gate basically for every output of the decoder. So, and every AND gate. So let's make a simple 1-bit decoder. Hey, Mr. Godin, welcome. This is a guy from the forums.
Yep.
Cool guy. I like him. I'm just joking. That guy's a dick. Anyways. All right. So we need 1 for every output. Well, let's make a 2 to 4 decoder. Let's splurge here. So we'll do that and that. There we go. Now, what we're gonna do here is...
Cheers. Haha, back at you.
I wouldn't have it any other way. So we got our input lines, 2 input lines here. So let's say that what does this thing default to? I think the top one is the low order and the bottom is the high order. So the top is the address.
I want to say the other way around, but
Is it the other way around? I could have sworn it was not that way. Wait.
It's been a couple weeks.
Yeah. It's only been like one day and I've already forgotten. My brain is shot, honestly. All right, let's wait. Let's open. I'm gonna give you guys a little sneak peek here into what I've been doing in the CPU world. Yeah, so low order is on the right here, and can I get one? Can I get one where it's like low order is on the top. So Papa was right, and I'm a retard. Anyways, let's. Okay, so low order top.
Lower or top?
Okay, good. Okay, top and then bottom is high. Okay, good. Anyways, what we're gonna do is we're gonna wire all these up here and wire this up like this. So we're just connecting these top and bottom inputs to each of these AND gates, and then we just set the inverters on the inputs to the patterns that we want. So for example, 0, 0 should activate, low order is top. So 0, 0 should activate this one. So in here, we go negate this one and negate that one. That means 0, 0 will make this one true. And in here, we want 1, 1, 0 to activate. So this should be, the bottom one should be negated. And then 0, 1. And then 1, 1 will activate the bottom one. Let's test this out.
And you just put NOT gates on those, or
yeah,
what typically?
Yeah, it's basically, well, it's putting NOT gates, but when you actually look at the transistors, it just uses different transistors. It doesn't add any transistors to add these inverters on the inputs. It just uses, I think it just swaps P-type for N-type, or maybe it changes the layout. I'm not sure, but I'm pretty sure that adding inverted inputs maybe doesn't. Anyways, it doesn't matter. If it adds transistors, what you would do is you would generate at the beginning. You would generate the signal and the inverse of the signal, the NOT signal. You generate them both here, and then you'd only have 2 extra NOT gates to generate all of these NOTs. But I'm just going to show it here because it's easier to inspect and just look at. This one is inverting both. This one's only inverting the second one, so forth. So here we go. We got 0, 0. That's outputting that one true. And let's go to 1. And let's go to 2. And let's go to 3. It's about Papa. It's about, not Papa, Ben. Oh, I got you guys mixed up. Anyways, it's about 5 minutes in. You're not missing much. So there you go. Now you can decode these binary values into individual values here. Now there's one other thing, and that is you're probably going to want a control line in here that will allow you to, let's go number of inputs 3. Number of inputs 3. Good, it's not messing around with my I did mess around with my thing. You bastard. Alright, number of inputs. You're going to do it too, aren't you? 3. What we want is we want to be able to control whether or not we're outputting at all. So we want to be able to basically disable all outputs. So let me just make sure that this is still working properly. I haven't fucked anything up. Yeah, 1, 2, 3. Okay, good. Now what we do is we add in here a third line. We'll call this one the enable line. And I'll put that there. Good. And now if this is 0, doesn't matter what we get here. Output, nothing is output. And that is your basic 2-bit binary decoder. Let me just do a little bit here. There we go. So let's what are we going to do? We want to look at this thing here. Well, this is probably fine, right? It's going to be that. This is the This is going to be the 0 output. Just give me that. Good. Okay. So we can make a 2-bit decoder like this. Now what we can do, add circuit. Let's make a 3. I'm not sure. I'm just gonna make bigger decoder. I'm not sure how many bits it's gonna be. Decoder. There we go. And what we're gonna do is drag this guy into here. That's kind of small. Make that bigger. And we can cascade these decoders in order to make bigger decoders. So what we do, let me just make sure I can figure this out here. So each one of these is going to go into one of these. So I think we need 4. So this is going to be a 4-bit decoder. So each one of these is going to enable Papa, it's one of your brethren. It's an enabler. It's gonna go.
Yes.
It's gonna go into these guys. So these 2 bits, essentially. No, not these 2. These 2. These 2 here. We're gonna do. That's too close. I feel a little poke coming through on you. There we go. These 2 should. Why are you red? You're not supposed to be red. What? Let me just go into here quick. View bindic. Error.
Add an output pin. It's not connected. I don't know.
Wait, that's super weird. But I mean, it says it's connected right here. It's like, dude, it's totally connected. Oh, this is floating. Maybe, man, it doesn't seem right. That shouldn't make the error. Forget about you. We'll come back to you later. What we're gonna do is we're gonna go back to bigger decoder. Here it is. Okay, simulate, reset simulation. That didn't help. All right. Let's try this. It probably just wants more inputs. Let's try adding more inputs. Hopefully that'll solve the problem. If not, oh shit, stream over. Everybody go home. Shh. You're gonna move this over here and get a little more space. Okay, so these 2 are gonna be the high order bits. So the low order bits are gonna go down here. Needed to add an input on the
control.
Probably. Yeah, I guess that makes sense. We'll see. Low bits go here. Motherfucker. And so this is there. And this is already getting super ugly. There. There. And this is the low order. Yeah. High order. Good. Now, copy this, paste that. No! Ah, I can't drag it. It always happens to me. This is like the bane of my existence. I swear I spend like half my time in Logisim just trying to drag shit. Alright. Now, so there is the 4 input bits. Nicely arranged. Here is... Oh, there we go. It liked it. Give that man a cigar.
Gold star.
All right. And
How many more videos of these will you make?
I don't know. I mean, I guess it's gonna depend. I don't think I've been what I've been doing is I have been kind of going ahead. I couldn't help myself, and I've been designing a CPU, and I found that to make a fully functional CPU, it's not going to take that long actually. But after we build it, there's obviously going to be a lot of enhancements that we can make. So it depends. It depends on how I feel and how people feel. I would say minimum, it's probably going to be about, after this episode, maybe 3 more. And maximum, it could go up to like 10. It just depends on if people are interested or not. All right, so we enable this, and there we go. We get the output here. And then if we wait, did I say low is top or bottom?
Low should be top.
Fuck me. Okay, let's see if we can just select the ones we want. Just these ones. Yeah, it looks good. It looks good. We're gonna do it. We're gonna do this. Shit. Almost perfect. There we go. All right. Okay. Oh, it's almost perfect. It's just one more down. There we go. Okay. Here we go. Let's do this shit. Okay, so we got 0, 1, 2, 3, 4, and you get the idea. So there you can make a 4-bit address to 16-bit selector decoder thingamajig. Super good, right?
Looks good so far.
Yeah, it works. So now that we can make it, we say we're never going to do this again. And we're just going to use the decoder here. Because, you saw all the logic gates that go into that. If we had to make all of our components in that way, the fucking simulation wouldn't be able to run. The simulation here can only run at a maximum of 4.1. The clock can only run at a maximum of 4.1 kilohertz. So it's not that fast even to begin with. But if we throw in a whole bunch of logic gates, this shit is going to slow down. This program is written in Java, by the way, and it's single-threaded, so... Let's go... let's go where? Let's go to RAM. Let's get rid of this stuff. Stop it. Go away. Remove circuit. And remove this circuit, because we're done with it. We'll go to RAM. So like I was saying before, now we can decode stuff. So let's make an 8 memory location RAM, 3 bits of address space. So we got 3 select bits here.
Joe Schroeder said he had to make one of those in Minecraft.
Really? With the redstone.
Yeah.
I always found that, like, when I first heard about that, I was like, that's actually pretty sweet. Have you played Minecraft?
Oh yeah.
I've never actually played Minecraft here. I'm revealing myself as not a true gamer, but I've never played Minecraft. But I've seen that redstone. Like, that is actually pretty sweet. I would be down for that.
Except it definitely runs a lot slower than 4 kilohertz.
Yeah, I would imagine you probably can't. But just the fact of making like a fully working CPU in that would just be amazing.
Yeah.
Have you ever heard of what is that? I think it's called the Babbage difference engine or something.
Doesn't sound familiar.
I gotta wait a minute. I gotta use my brain for a second. I can't talk to you. I have to think. I can't do both at the same time. These operations are not. There we go. Okay. No,
now you said it would slow down your computer. Have you tried?
Yeah, I have tried. Well, I tried with my my whatchamacallit, my CPU that I've been running.
Yeah.
And it's simple 8-bit CPU with just the stock components. So not like doing everything from basic gates, and running at full clock speed. It brings me to about 70-80% of my CPU, but I haven't implemented all of the parts of the logic or all the instructions yet. So I figure when I'm done, it's probably going to be around 100% at whatever it is, 4 kilohertz.
Wow.
So if I had to instead simulate it with individual logic gates, it would definitely go over. I wouldn't be able to push 4 kilohertz. I think. I haven't tried it yet, so I can't really say for sure. But, all right. Now that I've done this, I'm going to delete it all. Okay, what I want to do is I want to make a single, what is it called? Like a cell, I guess? Single memory cell. So what we want here, we got the clock, that's going to go in here. The enable is going to be coming from the decoder. We're going to need a data bus. So, it's no good. Let's just drag this out. We're going to make this into the data bus. So this is going to be bidirectional, by the way. So signals are going to be coming in and going out. So we're going to need to make tri-state inputs on this. So let's do that. Let's make a tri-state gate. Controlled buffer. There we go. Yeah. All right, and this is also going to be controlled by the old decoder. And the way you're going to determine whether or not you're going to be taking a value in or outputting is you're going to need another control line, or you're going to need a control line called the read-write line. So just say that is that line. Read-write enable. And we'll just make this one the clock line, I guess. This is clock. Clock, read-write enable. What else do we need? I guess we just need a general enable. So we need read or write select, and then a general enable line just to enable the memory. No! I guess I can't copy and paste that. So what I'm going to do here, make another line. This will all become apparent in a second. Just setting up a little bit of infrastructure here. You ever play any city building games, Papa?
A long time ago, I played SimCity, SimCity 2000.
Oh yeah, I spent a lot. I didn't play much 2000, but I played like the original one on the Super Nintendo. I played the shit out of that game.
Never played a console version.
It's actually surprisingly pretty good. Like you wouldn't expect a game like that to be decent on. I really liked the SimCity, and on the Super Nintendo, and I liked Civilization on the Super Nintendo. Believe it or not. Ah, fuck you! You just deleted my line. Oh, you bastard! I should be using the wire draw tool, but I'm gonna be smart. I'm not gonna switch it. I'm just gonna use the tool I've got, and I ended up wasting way more time.
Sim Gunther brings up a point. It says unless you pipeline a couple commands simultaneously, it can only go so fast. ARM CPUs for the win. Is your processor going to be pipelined at all?
No, it's not going to be pipelined. There's no pipelining involved. But I will be able to. I think I could probably get every instruction, or mostly every instruction, to execute in one clock, which is pretty good. Because the original 8086, like the average instruction per clock was maybe 10 clocks per instruction or something, something bullshit like that. So, but no, we're not going to be doing any kind of weird designs. We're not going to have any translation look-aside buffers and page memory, and there's going to be there's going to be no branch predictor. So, at least not to start with. You never know what's in it for the future. Okay, fuck. I gotta concentrate here. Gotta get my game face on. What we want. Okay, so this going to be connected to the data line directly. I think that's acceptable. And there's this. So we're going to need some logic to determine how to control these lines. Clock is just put in there like that. I think that's pretty good. So we've got. I'm going to so I don't forget, because I know I will, I'm going to put some words here. The lines are too close together. The words aren't going to make sense. So this one is going to be read /n write. So if it's if it's low, that means we're writing, and if it's high, it means we're reading. And that's this line here. And where is it? Give me some more text. This one is going to be the enable, or it's actually usually it's called select for RAM chips like that. Chip select. So that's what this is going to be. That's just to tell this RAM what we're going to do something with it. Here's our addresses coming in. So this is a wait. This output is 3 bits. So this is actually 3 bits in here. Wait a minute. Maybe I don't need an enable here. I think this is actually an enable in and of itself. Enable. When not 0, selected output is 1. So we could leverage that so that we don't need this. Yeah, I think that's doable. Get rid of that. Yeah, there's actually no real reason in Logisim to use a cache because all the memory is the same speed, right? The registers and the RAM and everything, it's all the same speed. So cache doesn't make any sense in that case.
Finish Let's Play Shadowrun, Sega. The sake of...
I've been that's been just sitting around there for the longest time. Because when I actually originally made that series, I was like the only person to ever cover that on YouTube. So, it was a thing. But now there's actually some, there's some amusing stuff on there, more amusing than me. So I figure it's kind of like defeating the point.
I think I watched one episode of your Let's Play, and it was Shadowrun.
Oh, you watched only one and you stopped? I'm so hurt now. I think I need a moment.
I was more into your tutorial series, so.
Fair enough. I understand. I will not hold that against you. All right, so here we go. So we only need this read write. So when we get an enable from here, a selector, a memory cell selector, what we want to do is we want to combine that result with this to determine. Okay, so what we want to do is we want an AND gate. Good old friend AND gate. Always there to help. We're going to say we need this and this. So if we're trying to read and we're enabled, then we want to put this on the data bus. Sounds fair. Does that sound fair to you, Papa?
I didn't follow.
Okay, that's good. That is good. Okay, so if this line is high, that means we want to read something from memory, correct?
Where's the pointer? Okay.
Yeah. And if this line is high, that means that we're trying to access this cell of memory.
Okay, so that's okay.
Yeah. So if we want to read and we want to access this cell of memory, we've got to enable this data to go on the data line. How's that strike you?
All right. What's the little triangle?
Oh, that's the tri-state buffer. That just means if this is low, then this value cannot reach this line. It's disconnected. And if it's high, it connects this to this.
Okay.
So it's a programmable or a selectable connector. Because you can't just connect things directly to the line here, because what if something else is trying to drive this line and this is also trying to drive the line, then you've got a short circuit and then you've got fried components, right?
Right.
So what you do is you put this tri-state buffer in here, and now it allows you to selectively connect different parts, different nodes in your network to each other. So that is for the read portion of our program. Now for the write, if we're trying to write to this mother, what we want to do is very similarly go like this. And now what we're saying is not this. So we gotta go negate left. Yes. Ah, I don't like that. Let's get rid of that. There we go. And this. So this one will turn the enable on. This one will be off because it's the complement. If this one is on, this one has to be off. And that will allow the data on this line, which will be driven by the CPU, to go into this register.
Mm-hmm.
And that is a single cell of memory. Yeah, Robert's got it right. I mean, the cache allows the CPU. It gives you some memory that runs at the same speed as the CPU clock speed, and that's a good thing. But the only reason why your memory doesn't normally run at the CPU clock speed is because most memory is. Why is this not the same as this? 8 databits, 1 databit. Okay, here we go. 8. We want 8 databits here. So most RAM is DRAM, right? Which is just a bunch of capacitors. And it's way slower than RAM built out of flip-flops, which is what cache is. It's basically RAM built out of flip-flops. Not exactly, but I mean close enough. But the problem with RAM built out of flip-flops is takes up way more space, so it's got lower density. You can't store as much with it. So we take our bulk RAM, the stuff that we call RAM generally, and we build that out of dynamic RAM, DRAM, and it's slow. And then for the really fast cache, we build that out of flip-flops. We put that right on the die with the CPU. But in this program, everything runs. There's no limitation on speed. Everything runs at the same speed. So there's no reason to make a cache from a memory speed point of view. All right. So we're gonna do like this, and now I'm thinking maybe I don't want. I could do it. I just gotta zoom out a little bit. I was thinking maybe I don't want to do eight memory locations, because then I have to that's a lot of work. I don't want to have to copy and paste that much bullshit. But we can do it. We can do it. We just gotta extend this a little bit here. Yeah, there we go. We can fit a bunch in there. Maybe not 8, but we can fit a lot. All right, so we're gonna take our memory block there, copy that here, paste, copy that here, paste. Hey, Papa.
Mm-hmm.
Have you ever heard of DDWRT?
My mind's drawing a blank. DDWRT.
It is it's like I don't know what you call it. It's not like an operating system. It is alternative firmware system that you can install on your router. And it's basically a Linux distribution that you install on your router. It replaces the stock firmware. And you can do like a whole bunch of bullshit with it that you couldn't do with the stock firmware. Lots of features that you can get that would normally cost a lot of money. And they're just software features, so you can just install that on a normal cheapo router and get like a pretty decent router.
Huh.
Yeah, it's pretty freaking sweet. I just installed it. I got a router off eBay and installed DDWRT on it, and I am liking the shit out of that.
I've got a couple routers laying around.
Yeah,
try that out.
Yeah, you might want to play on that. It's a Linux distribution, so I mean, you can install a whole bunch of different programs on there too. There's a whole bunch of. I mean, I haven't really done it. The only reason I got DDWRT is because I wanted to use dynamic DNS, and the stock router that I had, it only supported updating for pay websites. So I was like, well, they wanted you to to pay the website that they're affiliated with to use dynamic DNS, and I was like, fuck that bullshit. I'm gonna fucking just install Linux on my router. All right. Now we have some memory stuff here. Let's take a look at
If the router is supported, it won't explode if you crank up the power.
Yeah, you probably want like a router that is supported by DVWRT. And generally, I don't crank up the power because I don't know. I don't want to be a dick and like jam out my neighbors with too strong signals. But you could. I mean, it allows you to control the power of the transmitter, the transceiver. So theoretically, it depends on the hardware, of course, but theoretically, you could put out a lot more power than is actually allowed by law, and possibly cause a big nuisance for your neighbors. But I mean, I just want to use dynamic DNS without getting effed in the A by by the maker of my router. Okay, we're gonna put some inputs on here. Input there. This is 3 bits input. And this one, you go to the north. And you go to the north. There we go. Okay. So, now comes the moment of truth. Does this bullshit actually work? We've got 6 memory locations because I was too lazy to make the last 2. And what we're going to do is we're going to try an operation on this. So we're going to activate the memory chip. How's it look? I guess it looks okay. Wait. Let me think here. One of these should be...
So yeah, I thought one of them should be on.
Yeah, I'm like thinking one of these should be on. Maybe I fucked it up. Yeah, this is wrong. This is very wrong. Okay, so we missed connecting one thing here. We missed connecting this enable input into... This has to be connected to this. Ah, shit. I should have done this before I copy and pasted all this bullshit. Should be like this, right? This enable should go to here and to here. Instead, it's connected to the clock, which makes no sense. I don't know why that happened. Probably copy and paste bullshit. Well, we're just going to quickly rewire all of these mothers. And yeah, okay, there we go. Now we've got some stuff enable. So this right. So it's not right. Wait, that's here. This is the clock. So this is read not write, and now it's 0. So it's in the right. It's in write mode. And that means that the enable should be high, and it is high. And now if we put some data on the bus. This is annoying. I am not sure. Okay, I got it. I gotcha. So we got to simulate a CPU driving the bus here, otherwise it's not gonna work. Driving the bus. Reminds me of an old Simpsons quote. There we go. Okay, now we can selectively drive this bus. So let's try to write something to memory. We're going to drive the bus from the CPU. We're going to set a value like that. We have set to write mode. We're selecting 0 of the address. So we clock and we look. And we have written something to memory. Now let's, I don't know. Maybe we can change it. We can change the address. Let's go to address number 123. I didn't have to do that. I should count here. 6. So that is 0. That's 5. 4, 5. Yes. We'll write FA on there. And then if we wanted to read from 0, we turn on the read, select 0, and turn this off so that we're not driving from the CPU. And then we get the data stored in memory location 0 appears on the data bus right here, which is what we put in there. And there you go. You've got nice simple memory module. Nothing too hard about that. Anything that bewilders you, Papa?
The operations? No. No, it looks pretty straightforward.
Yeah,
Yeah.
I think so. I hope no one else no one in the chat is lost and afraid, naked and afraid. Well, I mean, you could be naked. I wouldn't tell. I mean, I could be naked right
Just don't
now.
be afraid, right?
Yeah. I'm not gonna say either way whether I'm naked or not, but I'm gonna tell you that I'm not fully clothed. That's for sure. Was that too much information already? I don't know. All right. So now that we've got this, wait. I want to delete it now. I want to remove that circuit. There we go.
Well, it is a little after noon on a Saturday. I don't blame you. For you.
Ah, for me. Yeah, that's true. I guess I didn't think about it that way. You guys are maybe a lot of people coming off of work or school or something. Where's my RAM? Memory RAM. So this is what we're going to be using in our actual CPU. It's the RAM unit. It's way better than the one that you can make yourself because it gives you a window into what is actually in there. But again, it's very similar. You got your address, you got your select, you got your clock, you got your load, which is your read-write signal, and you got your data. And you also got another signal here. You can asynchronously clear the entire memory if you wanted. Not really important. But that's everything I showed you right there. And that, my friends, is memory. Another thing to tick off the list there. And we'll be incorporating that into this circuit a little bit later. But first, I want to talk about one more pretty important circuit element, component, if you will. And that's the multiplexer. What the multiplexer lets us do is it lets us select between multiple inputs, and the output becomes one of those inputs depending on, again, some select bits, which are just address bits, address lines, if you will. So this is an alternative to our solution of, where is it? I guess I should do it the standard way. So what we want to do is...
Sounds a lot similar to a bit mask.
A bit mask. Yeah, I guess, yeah, you could see it as like a bit mask. True. Bit masks, actually, it's probably like an analogous operation to a bit mask. Now I'm thinking about it, because multiplexer is just going to use logical operations, and a bit mask just uses logical operations. So yeah, actually, it is exactly like a bit mask. I was going to say something else. I was going to say it's basically going to replace our tri-state buffers that we use to select what goes in. But from a mathematical standpoint, yeah, it's a bit mask. Okay, so we'll just use two input guys like this. And what are we going to do here? Why are the data... Did I change the data width, or did I do something? There we go.
Joe wants to know, why would you need a multiplexer?
Well, that's actually a good question, because I've asked that question myself. I'm like, why would you need a multiplexer when you could just, connect like a bunch of tri-state buffers to a bus and just select which tri-state buffer you're driving the bus with? And the reason why I'm using a multiplexer is because it's going to make our circuit diagram less messy, and because it'll use less components in the simulation, and so it'll allow us to run the simulation faster. But from a pure designing actual silicon standpoint, I'm not sure why you would ever use a multiplexer instead of a tri-state buffer. I mean, the only reason I can think of is the multiplexer, it's always going to be driving the bus with a logical value, whereas with tri-state buffers, you can have situations where two buffers are driving the same time, and in that case you get a short circuit, or you can have situations where no buffers are driving, and then you have a floating input. So you can have bad states on your bus with tri-state buffers. With a multiplexer, you've always got logic 1 or 0 coming out of there. Maybe that is, in some situations, that kind of stability is useful. I'm not sure. I'm gonna plead ignorance on this case here. And I'm just going to say that personally, I believe tri-state buffers to be more efficient, but in our situation, multiplexer is going to give us a better circuit diagram, probably better simulation characteristics in terms of performance. So, the good old fallacy, with the PH, my favorite. Phallus.
Logical fallacy.
My friend in high school, he amused himself by creating a. I believe he used just chemical names. He created a new chemical, which was like spelled out phallus, and I don't know. He found that incredibly amusing at one day in chemistry class. I don't know if you could actually do it with the real chemical names. You might have to make some up. Kind of like the Breaking Bad title cards, but let's see here. All right. So you got two inputs here, and you got one selector. So we'll set 1 to 0 and 1 to 1. So if the selector is 0, you're going to select the top one, and if it's 1, you're going to select the bottom one, right?
Okay.
Let's select the bottom one here, top one. Now we're selecting the top one. This one doesn't care. That's a multiplexer. That's all it is. 3, or depending on how you're counting, 4 logic gates. And similar to our friend the encoder or decoder, you can we can go here, and you can go like this. Wait, which one is this? Oh, this multiplexer is kind of dumb. Here we go. What is that? We don't need that. Include enable? No. Ugh. I got the wrong one. Here we go. So what we can do is cascade multiplexers like this and create multiplexers with more inputs. So we just connect the inputs of the multiplexers on the same level to each other. This is a different level, so this is going to be the high order. This is the low order, which is backwards again from what it should be, but bear with me. And we'll go like that. For completion's sake, I will just quickly demonstrate. There we go. Copy, paste, paste. And we get our output here. And we get our this one there. There. Okay. And now we select 0, 0. That means that this is the output. These ones don't matter. Don't matter. Don't matter. We select 1, 1. This one's the output. Don't matter. Don't matter. Don't matter. Again. And if you want to make, for example, if you want to make a multiplexer that is, this is selecting 1-bit values, right? If you want to make ones that select 2-bit values, all you do, stop it. Just stop it. No.
It's going to take your mistake with it.
There we go. Copy that, paste that. Yeah. All you do is you just, you line them up in parallel, and you put these ones together. These are going to be the, the 0 input, the 1 input, the 2 and the 3. You line them up like that. You arrange them in parallel. It's the same as with logic gates, right? You can arrange them in parallel for creating wider data bits, or you can arrange them in cascading, and that'll give you more fan out, more inputs. It all works the same. Sim Golter says Boolean matrix multiplication. Why do you say that? Is there something in there? Am I missing something? Is there some correlation between multiplexers and Boolean matrix multiplication? I guess there probably is, but I don't get it. I'm dumb. Now, one more thing I just want to say is what you can do with a multiplexer is you can use a multiplexer to implement any arbitrary function, Boolean function in here. So what you can do is let's set the select bits to 4. So now we've got 16 inputs here. And so you can take a function of 4 input values in the select bits, and it will select one of these as an output of that function. And you can set these to whatever value you want using wiring, power. So if you set this one to 1, that means that an input of 0, 0, 0, 0 gives you an output of 1. And you can set these ones, this one to ground or whatever. And you can create any arbitrary function you want out of a multiplexer. And the reason why I'm saying this is because that is how FPGAs work, I think. I believe. At least when I was in university, that's how they worked. And I don't think they've changed. So what you have is you have a whole big array of multiplexers. And these inputs are all connected to SRAM blocks. And every SRAM is configurable, so you can configure the function of every multiplexer, and you can configure the interconnections between multiplexers, and that is how you synthesize any kind of digital circuit in an FPGA. Not important for what we're doing here, just some bullshit trivia. All right. So there we have it. We have our multiplexer. We have our RAM. I don't know why I went here. Let's go to our ALU. No, let's go to our top circuit. There it is. So what I want to do now is I incorporate that into here. So how are we gonna do this? I want to lay this circuit out so it's gonna be nice and sexy. Don't want any of that. I don't want any trashy circuits here. I want a classy circuit. So we'll get a little more space here. Space is important for reasons.
So are you doing this as a demo reel for for trying to apply to Intel or something?
Yeah, I think they'll be really impressed by my 8-bit scalar CPU here.
Well, you got to start somewhere, right?
Nah, I believe that ship has sailed. I'm now an old dog. I'm unable to learn all the new tricks. All right. I'm just gonna delete all this stuff. Just die, because you are just gonna make my life difficult. I want lots of room in my inputs, so I can build around here. Also, let's just move this down a lot. We'll give ourselves some space, because that is the thing you run out of the most when you're designing space. All right. So what we're gonna do about these motherfuckers? Sub, add sub. All right. So first off, I don't like the situation where this line here selects add or subtraction, and this one determines whether it is subtraction or adding. So these two in conjunction select add, subtraction. I don't like that. I want every single individual line to select a different operation. So make a one-hot encoding here. So what we're going to do here is we'll just insert a little bit of logic. Turn this one into add. No. Yes. Add. This one will be subtract. Okay, that sounds good to me. All right, so add. That turns this one on. Subtract turns this one on as well, but it also flips that. So what we're going to do, put an OR gate in here. So now we can enable the adder with this, or with this, we enable the adder and we invert the input. There we go. Now we're going to go into here and we're going to change this to just add. There. Perfect. One problem solved. We'll go back. Let me out of here. Let me out. Will this work? That doesn't work, does it? Does this work? There we go. Okay. now that we have these all one hot encoded, we're going to get rid of that because that's way too many lines to worry about. We want fewer lines, so we're going to use plexer a decoder here. And we want select bits 3. I'm wondering now whether I should add an extra select bit because I might want to add more operations later. But, fuck it. That's good. We'll cross that bridge when we come to it, and we'll probably regret our decisions when we reach that point. But until that point, we will be blissfully oblivious. There we go. We don't want an enable input here. We just want to always be outputting something. No, wait. We do want an enable input. I lied. Because if we don't have an enable input, it's always going to be selecting one thing. Well, does it matter, though? Does it matter if we select something or we select nothing? Let me think here. No, it doesn't matter. This one can always be driving this bus. This bus is completely owned by this ALU, so nothing else can ever drive this bus. The way we're going to get things from the memory onto this bus and into a register is we're going to pass it through these inputs. So the memory is going to be passed into here, through here, and into the registers. That's fine. That's good. We are set.
Some load and store operations.
Load and store operations?
Yeah.
Yeah. It's basically load and store is just going to be add with 0, right? And that is how we're going to solve that problem. All right. So now what we want to do is we want some multiplexers over here. Now this one I'm also going to put in 3 select bits, even though we don't need that many right now. Enable, no. This one I am almost certain we're going to be extending in the future. Now why did I do that? Why did I do that when I obviously need to change data bits to 8 first? Then I do that. Alright, so these are going to be our inputs into A and B of our ALU. And 3 bits each. And we'll just kind of get these guys out here chilling. What else do we want? We want registers. We definitely want registers. You know what? I want even more space. I just want all the space. Give me all the space. Move that over there. Okay. Now, 2 registers. We're only going to have 2. Memory. Register. Alright. I haven't decided what to call these ones. I don't want to call them A and B, which is what I called them in the other one, because we already have A and B for the inputs to the ALU. It's confusing. What do you think we should name these registers, Papa? I'm giving you the honor of christening our registers.
Okay. I don't know.
Damn it, Papa! You're letting me down.
The only thing that comes to mind is stuff that I've heard, like EDX or EDA, EDB.
Ah, yeah, that's the the x86 registers.
Right.
Yeah, that's also A and B. You can't use A and B. I just told you that. Why you got to be so contrary all the time? All right. So we
Adam and Eve.
Adam and Eve. That is also starts with A. That's still unacceptable. All right. Let's see here. So we've got A input here, B input here, ES, SS, DS. Those are segment registers. Jesus Christ, man. All right, here we want to input. We want that's fine. We want to put a 0 in here. So we can do that a number of ways. Just put ground, I guess. Ground is fine. Data bits, data. There we go.
Okay, bro.
Do you know, Papa? Are you aware of the registers DS, SS, CS, ES?
No, I'm not.
Yeah, they're mostly a 16-bit thing, right? They're the things that allow you to address more than 16 bits of memory. They give you an extra 4 bits of address space. But I mean, now that we have 32-bit and 64-bit with we can now have big pointers. We don't really need the segments.
Is that where Microsoft got or not, maybe it's not just Microsoft, but long pointer?
Yeah. Well, I mean, yeah. When you go to 64 bits, then yeah, the different data types to distinguish standard pointer from long pointer. So yeah. Actually, in 32 bits, the SSDS, they have a special bullshit use that I'm not even completely sure about. In protected memory selector. You got a descriptor table. It's weird bullshit. I want to try it out though sometime. But when you get to 64 bits, they just throw all that garbage away and they just say, we don't need this bullshit anymore. All right. So this one is going to be for passing through a value from RAM. So this is going to be driven from memory. So we can connect this one up into the memory bus. What else? What else do we need here? Data. These two are connected together. And they are going to be also connected to here. Yeah, that's how that works. And this is going to be connected to the memory data bus, the external data bus. Stop it. And we'll just, I don't know how much space we need here. Let's make a little bit more space. We'll call this the external, stop it, the external data bus. Right here. Get rid of that. And this, you go away. This is how we're going to connect our registers to the memory. We need a gate here. Controlled buffer goes in here like that. And it's 8 bits. So that is how we're going to be allowing the ALU to drive the external data bus when we want to write values to memory or to other external devices, which we will have, like a monitor and a keyboard. What else do we need? Okay, so one thing that we definitely need is... let me look at this here. Well, let's put in our memory first of all. I was planning on creating a block diagram for the CPU and then having the memory external to the CPU in another block diagram and connecting them together. But actually, in terms of debugging, it's nicer to have the memory in the same circuit diagram as the ALU and the logic, because then you can just quickly look over and see what the values it's accessing are and see what the value of the register is. Whereas if you had an external diagram, a top-level diagram with memory and CPU and address decoder or whatever, then it would be a lot more difficult to debug this bullshit. So I'm just going to stick it all in the same diagram to start with. So this goes on the RAM data bus. That just connects directly to the bus. Now here's the thing. Address the thing that's usually going to be driving the address bus is the instruction pointer. That's the register that holds the address of the current instruction. So we need a register for the instruction pointer, but we don't want just a standard D register. What we want is we want a register that is able to increment itself every clock cycle or whenever we want it to, because generally that's what the instruction pointer does, right? It increments every instruction to load the new instruction, to point to the new one. And we don't want to have to increment this by passing it through the ALU, because that's going to be a pain in the ass. We can do it without passing it to the ALU, because you can create a register that is able to increment itself. It's called a counter. So we're going to make a binary counter. Make an add circuit. Counter. And memory. So we can make a counter out of T flip-flops, which are toggle flip-flops. So we'll make a toggle flip-flop first. Toggle flip-flop is just your standard D flip-flop. Add a multiplexer. Select bits, one select bit, one data bit here. No enable. And we're going to make it face the opposite direction. Get a little feedback going on here. And there's two inputs. One input is Q. One input is not Q. We could do it, actually, we could do this even easier. Make two data bits. All right, here we go. So this input is not Q. This input is Q. And this input are going to be, this is going to be our new D. This is data. So you want a toggle, you want a flip-flop that you're able to do two operations. Toggle the value, or load in the value that you specify. So this is going to be the line for loading in a value. This is going to select what operation we want to do, whether we want to toggle or load. This feeds back into here. Enable. We want this just to be always true, so we'll just leave that blank. That leaves it always enabled. Here's the clock. Yeah, let's see if we can make some magic happen here. Data bits 2. There we go. All right. So the low order here, I'm just trying to get my brain straight. Low. So if this is high, this is the toggle input. If this is high, that means we want to toggle. If it's low, it means we want to load the value from here into here. So what's going to happen is, let's say you want to load a value. So we put the value on here, and it's going to select one of these two inputs and pass it through to here, and then load it into the register. So if this is low, we're always selecting this input to go into the data. So we're always just loading if this one is low. If we turn this high, now we're selecting one of these two inputs. And what are these two inputs? Well, one of them is, wait, shit, I fucked it up. Sorry. What I want to do is, all right, so actually, now that I'm thinking about it, I don't know why my brain actually just kind of stopped working for a second, and I thought that I could do something that I couldn't. Let's just wind this back for a second. Let's just forget about the last 3 minutes. They never happened. That was just a figment of your imagination. and we're gonna go here. All right, this is better. This is much better. Now we're approaching something that is sane. So what we've got here is, let me think here. This is the toggle selector. So if we have this true, every clock cycle. You're making a liar out of me, fucker. Wait. This thing doesn't have not Q. Wait a minute. No, it does have not Q. This is 1. This is 0. Oh, because I didn't turn the enable on. So you have to enable the flip-flop, otherwise it's not going to change at all. So if you enable the flip-flop, then you're enabling the value to change. This enables toggle mode, which means whenever you clock, it's going to switch from 0 to 1, 0 to 1, 0 to 1. Doesn't matter what this is, it's not being selected. If you select this to 0, that means you're in load mode. When you clock, this value gets put in the register. So if it's a 0, now it becomes 0. If it's a 1, it becomes a 1. And if this one's on, toggle. If they're both on, it just toggles. Toggle has precedence, I guess. Priority is what you want to say. All right, so this is a toggle flip-flop. That was a little weird, but we managed to get through it. Wait, I forgot to ask, Papa, are you lost with the toggle flip-flop?
I have no idea.
Okay, that's fair. Let's go over it once again, just a little more gently. So, the enable input, you get that when enable is 0, no matter what you do, it's not going to change, right?
Okay.
That just disables the changing of the flip flop.
Okay.
All right. Now enables 1, we can change it. Now there are 2 modes for this flip flop. One mode is the load mode. That's when this is low. In the loading mode, it takes the value here from data and puts it in the register. So if it's a 1, it becomes a 1. If it's a 0, it becomes a 0.
Okay.
Now the second mode is the toggle mode. If we turn the toggle mode on, this input doesn't matter, and the register, when you clock, it just flips its value. So we clock it, becomes 0. Clock it, becomes 1, 0, 1, 0. That's toggle mode.
Oh, okay.
Load mode, toggle mode. How's that for you?
Works out a little better.
Good. See, this is why you're here. Well, of course, for your colorful personality, but also just to make sure I'm not, talking complete bullshit that no one gets. All right. Let's get out a toggle flip flop. Are you kidding me? This is utter bullshit.
What?
The toggle flip flop doesn't have a data in, so that means that I can't do the thing that I want to do with just the toggle flip flop. All right, well, we can roll our own toggle flip flop for the moment being. We'll just use this, and the output. Wait, the output is here. And this is the inverse of the output. There we go. Copy that, paste that in there. Good. So now, this is data, toggle, clock, enable. Gotta remember that. All right. Data, toggle, clock, enable. Move that like that. Just go. Go up one. There we go. Okay. All right, we can make this work. All we got to do is go project, and we'll make a counter. Wait, Sim Gunther is what? What's up? What's up, Gunther? What What is ailing you? Counter. Wait. Oh, wait. Did I already add counter? Oh, this is counter.
Did, yeah.
Well, shit. That was a toggle. That wasn't a counter. What is going on here? All right. So we want to add some toggle circuits into here. And we're going to make a 4-bit counter. I may or may not regret the decision to make it this wide, but it's probably fine. All right. So when you increment, here's the fun part. Now I get to explain this bullshit. There. All right. Wait, I can do something here. I go to OBS. I go to oh, it was already in Photoshop. Shit. It was supposed to be in Logisim. Anyways. Well, no harm done. No one complained too hard. Let's get rid of that.
Meant on the no data input on in toggle. That's what the what was for.
Ah. Maybe I think I said something dumb there too, like something about priority, and it didn't actually make sense. I think maybe that's what he's referring to.
No, he just said that he was talking about the no data input. When you said there's no data input on the toggle.
Oh yeah, yeah. Okay, I get you now. And I am also very disappointed in that.
He's agreeing with you.
That's good. Agreeing with me is always the best way to go, in my opinion. Okay, so when you're counting in binary, what you're going to notice, no, that was a failure of the counter. 0, 0, 1, 1, 0, 1, 0, 0. What do you notice about the thing I'm pointing to right now, Papa? No. He can't see my pointer in Photoshop because of, I don't know, reasons, Skype reasons, I guess. Anyways, what do you notice about the bits in the low order bits as we count?
They just flip back and forth.
Right. So this is why we need the toggler, because counting is flipping back and forth. And the pattern of flipping is, so here it flips every bit. Here it flips every other one. So flip.
Oh, yeah, every other one, yeah.
Don't flip. Wait. Flip. Don't flip. Flip. Don't flip. So every second one, right? And then here it's going to be every fourth one you flip, and so forth.
Right.
So this is why I had to, talk about the toggler, because toggling is flipping, right? Now, what we're going to do, I've already forgotten which pins go where.
The top one is data.
All right, yeah, top one is give you a data, toggle, clock, enable. Okay, you got to remember that, Papa, because I'm not going to remember that shit.
Data, toggle, clock, enable.
All right, good. Let's go back. First of all, let's do the thing I was supposed to do. Is switch to Logisim mode, which is almost the same but a little different. And now, go back. How do I go back? Go here. There we go. Okay. Data, toggle, clock, enable. So we want to connect all the clocks first of all. That is just synchronous computing 101. There we go. Clock. Done. Let's get an input on there. There we go. All right, now the data, we don't need that yet. We're gonna save that. We're gonna save that spicy meatball for later. Let's go down. There. Good. Data, toggle. Okay, toggle is this is where the magic happens. Enable. And those are all tied together, I guess. So we'll put them down here as another control type input. I'm going to copy that. So top one is clock, bottom one is enable. These ones are the data for just loading in here. Here's the output. This is the data out. We'll do that later. We'll do this later. the important thing in here is this. So this is the toggle.
Right.
This is going to be part of enabling counting mode. So what we want to do is we want to, if we have count enabled, we want to flip this bit every clock cycle. So if I enable all the registers and I enable counting mode, so it's flipping right now. Good. Now, what we want to do is for this one here, get out my AND gate. We only want to toggle when this one is high and we're in toggle mode. What that's going to do is, no, you don't understand. You don't understand. That's not how it's supposed to work. Yeah, wait a minute. Let me think here. There could be a problem with the signal propagation. So this one is, when this one goes high, okay, good. No. This is fine. This is I was looking at the wrong thing. Here we go. So this is data bit 0. This is data bit 1. Okay. Just had a weird brain in episode again. They happen, you know. So 0, 1, 2, 3. 0, 1, 2, 3. Because this one is only going to toggle when this one's high. So it's only going to toggle half as fast as this one toggles, right?
Right.
And that just keeps chaining up. So what we do and copy this one to here. You go into here. And stop it. And you go, wait, that, and we have to be toggling. So they're all controlled by the toggle or the count input, not toggle, count. This is the count controller. No, wait. No. Oh good. I caught myself before I did something stupid. Right, because this one, any input, all right, this is good. Any input, the only time it toggles is if all of the bits before it are already set, right? Because you get a carry, and then toggle. So you have to check if this one and this one is set in order to toggle this one. So for this one, it only checks the one before it. This one checks the 2 before it. And this one, if you look, 1, 0. Ugh. As you can tell, I'm using my mouse now to draw.
All right.
0, 1, 1, 1. And then when all of these are set, then this one can toggle. So what we want to do is, well, this is conveniently already, I set it to 3 input. No. So this one has to check this, and this, and this. And this one would be a 4 input. And you want to check, no, stop it, this, and, wait, did I do something stupid? Probably. Let's check this one, and let's check, this routing is becoming a nightmare. And check this one, and check this one. There we go. All right. It's beautiful. Just gorgeous piece of computer-aided design right here. Yeah. And yeah. All right, I probably made a mistake somewhere in there. It's almost certain. Let's see where it is. This is the clock. So we go 0, 1, That's good. So far, so good. 2, good. 3, good. 4, 5, 6, 7, 8. Okay, never mind. I'm perfect. I'm a perfect man. There we go. So, and that is how you count. Counter register. Now, the other thing is you want to be able to load just parallel values into the counter, which is very important. For example, if you're executing a jump instruction, you want to be able to load the value of the new address into the instruction pointer. And that is just done. Nah. Let's just show it quickly here. Might as well. Papa.
Mm-hmm.
My hard drive died again today.
What?
I bought a new one, and it's, again, a physical hard drive, not a SSD, solid state. And the motherfucker just, same bullshit, just stops working, just drops out. And I moved it to a different controller on the motherboard. I can't tell why this motherfucker keeps dying on me. This must be Western Digital, because I bought another Western Digital drive against my, better judgment. I'm like, it's probably just a fluke thing. Fucking thing happened again.
So, when you say it just died, does it spin up or?
I can't tell. I mean, I haven't listened to it. All I know is that it doesn't appear when I rebooted Windows. I was downloading a possibly semi-non-legal piece of data from the internet. We're not sure. And anyways, it just stopped halfway through, and it just disappeared from the my computer thing. So I'm like, well, that happened before, and that wasn't good. But if I reboot, it usually came back, but this time it didn't come back. So I'm like, shit, son.
Something somewhat, I can't even say similar. As you know, I've replaced my motherboard a couple months ago because a lot of stuff was going on and thought it was the hard drive, but tried it in other computers and the hard drive was fine. It just at the end the motherboard.
Yeah, I mean, I would like to try this hard drive in another computer, but I haven't. The thing is the problem I had with the original motherboard, I've already replaced that motherboard when I replaced my CPU, and it's still on the same problem. And then I replaced the hard drive, it's still the same problem. And the power supply unit, I just want to fucking just take this piece of junk PC and throw it off my 4th floor balcony and just like, adios, motherfucker. But anyways, yeah, I have a SSD hard drive. I have 2 SSD hard drives actually. One is Intel, one is Samsung, and they're fine. They have no problems. But for like mass storage, like for huge files, I would like to have like a nice 2 terabyte drive that I can just jam that shit onto. So, anyways, this will enable the counting. We count. No, wait, what's happening? Wait.
Oh, wow.
That's weird.
Well,
No, well, that's it. Papa, you broke it.
I was gonna say, what did you do? You added the things at the bottom, and now it doesn't work.
This is in.
No, it's just flip-flopping between the two.
All right, that's. I mean, it's interesting, but it's not particularly useful.
No.
Did I cross any wires here? I don't think I crossed any. I mean, because I just added these here, right?
That's all I saw.
There must be something wrong with my counter then, because when I left these floating, here, let me try this. When I floated these, it worked fine, right?
Yeah, before you added them.
Yeah.
Yeah.
So
yeah,
these guys driving the lines somehow messes up my bullshit. I don't know.
It's messing with those are your data ins.
Yeah, this is the data in. Somehow the data in is fucking with my stuff here when it shouldn't be. I mean, this in here should have no Yeah, it shouldn't have any effect on what happens when the toggle is high. I don't know. But you know what? I'm going to say I don't care. I think I have sufficiently proven that we can make a counter. I don't know. What do you think, Papa? Do you think we should just call it at this and say we have made the counter, or do you want to go and debug this bullshit?
Interesting, but anytime you cross wires, things are bound to go wrong. Yeah, I mean, you've shown the principle of it.
Yeah, I think I've demonstrated the principle, and maybe because I don't want to go on stream and like be debugging this for like 20 minutes just to find my dumb mistake, and that's just bullshit. No one wants to watch that. Maybe what I'll do is I'll save this. I'll just keep this this circuit here, and I'll look at it maybe later, and maybe next stream I'll just quickly show you the error in my ways there.
Sounds good.
Yeah, no need to go over that on stream, I think. All right, so we've got a counter register. We designed it. It works perfectly, no problems whatsoever. Now what we're going to do is we're going to
import one of Logisim's.
Exactly. which has the exact same functionality, no difference whatsoever, of course. Yeah, counter. Here we go. So we've got our counter. It's got the Q and the not Q, and it's got data, count controller, and this thing here. This is the data load enable, which allows you to load into here. And right here, what we're going to need is another multiplexer. That's not a multiplexer.
That's a decoder.
Yeah. Another multiplexer as he grabs a decoder. All right. Here we go. So this is going to select what address is driving our memory. And for 0, 1, we'll put the instruction pointer at location 0, 1, 2. And 0 and 1 are going to be driving it from, where is it? Here it is. From our registers, which still have yet to be named, by the way, Papa. I mean, I don't want to get on your case, man, but you had one job. No, I'm just joking. I mean, I just call them X and Y, right? X and Y seems pretty good, right?
X and Y.
X and
Everything I think of that has an A or B in it, so.
Yeah, but the thing is, I would call A and B is the common one, but I in my moment of stupidity, I called these A and B. I guess I could just change the name of these ones. That's actually not a bad idea. Let's just go into this. Okay, we're gonna call this. We're gonna call this X. No, wait. This has to be Y.
Yeah.
Yeah, because that's the negating one, right?
Decoder, multiplexer, same difference, right?
Yeah. It's close enough, right? I mean, Jesus Christ, goddamn perfectionists here. All right, so I'm gonna switch these around here. So now, this is the inverting input, right? This one's gonna be Y. Why? Because I gotta. Remember that one, Papa?
This sounds familiar.
No comment. It's seminal Jim Carrey, Canadian celebrity extraordinaire, Jim Carrey. I can't actually remember how that starts though. It's something.
Why? Because I got. Man, sounds familiar. Just can't remember the reference.
All right. Well, I mean, I'm not gonna lie. I'm a little disappointed, but we'll just forget about it. Just forget this conversation ever happened.
What is that going on tonight?
Now I'm like all pissed for the rest of the stream. There we go. X and Y. Oh, the output's also X.
Can't do X and Y because your output is X.
No, it's not. That is that is your mistake. In this is clearly not. Wait, clearly not X. It's clearly
Z.
F. It's F. It's totally F. There we go.
Nice catch.
Nice catch. I don't know what you're talking about. I don't know what there is to catch. I mean, it's just stating the facts. That's all I'm doing. Okay, so here we go. We got our
mask. Okay.
Yeah. Gunther, how does that start? Is it like something? Why? Because I got to.
Yes, I was never a fan of the mask.
You were never the mask. It's so good though. It's got what's her face and. Wait, it's not Drew Barrymore, is it? It's Cameron Diaz. Cameron Diaz is the one in there.
Honestly, even movies that I did like, I have a hard time remembering references.
What kind of movies are you into, Papa? What is your favorite movie?
Oh God. Crouching Tiger, Hidden Dragon.
I've never seen that movie.
Really?
Wait, is that a John Woo film?
You got me.
Wait, Crouching Tiger, Hidden Dragon. That's Bruce Lee?
No. It's
This is after he died, right?
well, it's not Bruce Lee, but yeah, it's somewhat recent, back in 2000.
Ah, okay, yeah.
That came
Okay. I have to check that out. I've been meaning for some reason. I've been playing Enter the Gungeon a lot, and I've been meaning to watch Enter the Dragon, but maybe it'll make me a better player. What do you think? It's worth a try, right?
Sure.
All right, so we are almost done setting up our. Oh shit! What time is it? All right. We got time. We got time for this. We got one more thing I got to set up here. So when you make algebraic operations, you get something that happens called flags. Flags happen, and that is what you use to base your branching instructions off of. So we need to generate those flags in here. One of the flags is the carry flag, so we already got that settled mostly. Carry out flag from the ALU here. Other flag is the 0 flag. Where is
Chow Yun Fat was the main character.
I don't even. I have no idea. But I'm pretty sure it is a kung fu film. Hong Kong, correct?
It's somewhat, yeah.
Wait,
I don't know. Basically, Crouching Tiger, Hidden Dragon, House of the Flying Daggers. I think the reason I'm kind of more into the Chinese, man. They can make like some really nice kind of fighting love stories.
Racist.
Just profiling, that's all.
No, actually, okay. For a period in university, I was really into the like the Chinese what do you call them? Like martial arts dramas. And yeah, it's like a love story with a bunch of like fighting interspersed within. And I get you. I feel you, man.
They usually have such sad endings.
The one that I was really interested in is called Condor Heroes. I forget the name in Chinese. It's like because it's in Chinese and stuff, but
Right.
It was pretty good. I might watch that then. Crouching Tiger, Hidden Dragon, you say?
Mm-hmm.
What?
They just came out with like a second one within the past year or two.
I will check that out. All right. So here is the other one of the other flags that we need, and that is called the 0 flag. So when the result of any operation is 0, this one is true. So all we got to do for this one is just take our result, pipe it into this big old AND gate, and there you go. You got your 0 flag. And the other one, let me think here. I need to check my other circuit. Is it in here? No. Okay, file, open, and this one. Okay. We got carry, 0, and a sign flag. I'm not sure if we're going to need sign at all, but we'll just get it for old times. Sign flag, sign bit is just the high bit. That's all it is. That's a sign flag. If the result has the high order bit set, then the sign bit is also set. All right, so output here. Carry 0 sign. Good. Now, which one is which? That's the carry. Put that one there. I don't like it. You should start it on the freaking line like that. Carry. That's the 0. No. Yes. Put the 0 there. Put the carry here. And we will put the sign. There's one other flag that we need, but I'm not going to put it in right now. That's the overflow flag. And that one allows you to detect overflows in signed operations, but I'm not going to do it right now. I might not even like put in separate signed instructions here because it's a pain in the ass. Probably won't even use them really in any program we're going to make on this motherfucker. So this would be fine.
Just gonna use all unsigned.
Yeah, I mean, you can synthesize signed operations from unsigned if you really want to, but I kind of don't want to. So we're just gonna do that. Good. Top. All right, so we got our 0, our carry, and our sign bit. So we need flip-flops to hold those 3 values. And where do we put them? Kind of running out of space here. Guess we could put them here. I don't want to. I got more space up here. Stop it. Okay, what we're going to do is put this one up here. Ooh, beautiful. Good. All right, so that should be enough space, I hope.
Okay, yeah. Ang Lee was the director.
Cool. I may have heard that name before. I'm not really up on the Hong Kong movie scene.
What do you normally watch? Everything Japanese?
No,
I'm just playing.
Never watch Japanese movies. They're horrible.
I didn't want to say it, but
you know what?
they need to have anime writers write the movies.
It's like 90% just really cheap to produce, like love scenes where like someone's probably dying of some terminal disease or something, and just like really emotionally manipulative material that is incredibly cheap to produce, and still manages to drag in the box office numbers in Japan. It's not my cup of tea, you know what I'm saying? It's not all like that, but I mean, a lot of it is. Okay. So the enabler guys here, we're going to want you guys enable want you guys like something like this. Can I get you? No. I want you to go over here. All right. So we're gonna bring these guys together with a nice splitter, which is also a combiner. So this will be, wait. Shit. That doesn't matter. So it's going to be sign, carry, and then high order bit is 0. 0 carry sign. Good. This is important because some operations you want to save the status bits, and some operations you don't want to save them, or you want to overwrite them, or you don't want to overwrite them. So it's important to be able to control that. Let's see here. Time do we got? Getting close. Getting close to the end of the stream. Closing time. So what I want to do is I want to basically combine all of my control signals into one big fat signal over here. And that's going to be the output from my control unit. State machine type deal. And here is where this is where the address or the data from the memory is going to come in. That's where the opcode is going to be fed into the state machine. So opcode in and control lines out. But I just want to, gonna have to gather these all together. This one is going to go in there. Maybe I should probably fan it out in this direction. So like this. No, stop it. Like this, and like this, and like, no, stop it. Yeah, like that. Good. So this is how we want to live our life. Enable is also going to be important. It's already getting super fugly. But we're gonna power through it here. So we're gonna route that like that. All right, good. What else we got? We've got the control bits for the status. That goes there. The control bit to put the ALU output onto the data bus. We got, this is the control bit for the address. This is the control bit to increment the, no wait, that's the clock. That's the clock. Don't do that. The control bit to load the IP. Control bit to, yes, do that. No, this is data. Stop it. Wait. What is the, this is the, okay, this is the one. Good. Gotcha.
That's a,
data. We need a, no, this goes, this connects to the ALU. This is fine. This is known. Incompatible widths, 8. That's not the ALU. Thank you. Thank you for telling me that. This is the ALU. Good. So the ALU output goes into the load on the instruction pointer. Good. Good, good, good. This is the chip select for the RAM. Could just set it to 1, actually, because it's always going to be on. Later on, we might have to do a little something with the memory decoding, but for now, just that. That'll just be 1, but the load is definitely going to have to be controlled by the control unit. So we do this. I'll route that up in there. This is riveting YouTube, by the way. I think I lost Papa. He's like watching porn or something.
no.
Damn it. Didn't catch him. All right. And here we got the address selector So I think that is probably all the junk that we have to feed into. Want to connect. Okay. The other thing we want to do is we want to connect all the clocks together, which is right now we've only got a few clocks. We got one here, we got one here, there and there. So this is the clock. And we want to be able to reset the CPU to some starting state. So connect the reset pins together. We want to reset those to 0. What else? We want to reset definitely the... Stop it. Stop it. Want to reset these ones up here to 0. Where is it? These guys. Off by a little bit. There we go. You go to 0. You go to 0. And you also go to 0. Good. We don't want to reset the memory when we press the reset button because that's what we're loading our program into. That'll be counterproductive. This goes to the reset pin. Do want to reset the instruction pointer when we reset the computer. And finally, these guys all are going to go into their own little bus thing. I don't know what you call it. Like that. Good. So this is where these are going to be fed into the branching instruction unit, and it's going to check these to determine whether to take the branch or not. This, I am not going to do this on screen because it takes a long time, but I'm going to fit that into there. We'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 fan out. Bit. Oh, I did it. I did the bad thing. Stop it. Stop it. Bit fan out 11. Like that. And now what you got to do for this thing is you got to first you got to count all the bit widths of all these ones, and then you add them together and you say, okay, this thing has a bit width of, I don't know what it's going to be. Maybe it's going to be like around 20 or something. And then you got to go for all of these and you got to say, okay, bit 1 is 0, and this one is also 0. Wait, no, go. 0, 0, 0, 0. So that's 3 bits for here, and then that's fine. You got to do that for all of these. I'm not going to do that on screen. That's just going to waste everyone's time. Might as well, if we're going to waste time, just waste my time. But that is basically how... Wait, these clocks aren't connected. That's not good. It's basically how this motherfucking data path is set up. This is all there is to the data path. This one goes to here. Good. Yeah, I think that's it. That is the data path, and we will be after I finish the basic 8-bit CPU, probably add some other bullshit to the data path, like maybe like a stack pointer and a bunch of other fun bullshit. But anyways, this is the main idea of all the data path. This is all she wrote.
Wow.
Yeah, that's it. Zoom out. There she is. Now you can look at this. Here's some spoilers for those of you who don't want spoilers. Look away right now. This is the world we live in. I have to give spoilers for a digital logic design video. I guess I don't have to. I'm just doing it. Open. Why isn't this opening? Here it is, because it's already open. It's right here. So here's what it's going to look like with some logic units built in.
Oh, God.
This is the controllers that control the different instructions. So these 3 are for different versions of move. This one is for add and subtract, and this one is for branching. And these are going to control, these are the control lines in, just like I showed you before. When you fix all that bullshit, it looks like this. And you got your status, and you got your memory. It's basically the same idea. But that is a story for another day. All right, so I'm going to wrap it up and thank Papa for coming on again, keeping me company. It's always
fun.
a pleasure. Yeah, great.
Yeah.
Good times. And also, is there any questions before I go? I can answer a couple of quick questions if anyone has any. But if not, I am going to peace out of here. Let me get some water.
So you put a new video up.
Yeah, got some hug
Hugs.
stuff. I'd recorded it a little bit back, but I finally got the time to edit it up and send her out there.
Some parallax.
Yeah, it's a pretty simple topic. Nothing too complicated.
Robert wants to know when's the next stream.
Well, I mean, maybe not next week. Actually, I'll definitely make an announcement, but I think next week I might not do a stream, and I might instead stream the week after next. So that would be when?
27th.
Yes, for you guys the 27th.
Yeah.
All right, so tentatively I'm going to say 27th, maybe earlier, probably not later. Same time. But you never know. Yeah. Nah, parallax scrolling is a nice little easy topic after all that SSE stuff. Man, I really like that kind of programming, but that just burned me out a lot.
Man, it's not only do you have to think differently, but there's so many more lines of code to get it to do the same thing.
And yeah, and the way you write, I mean, maybe there's a better way of doing it, but it's a lot harder to debug as well. It's not as straightforward. I don't know. It's not as hard as debugging assembly code, but it's like in between debugging assembly and debugging C. It's not a fun time.
Yeah. It's probably just all because of the Indianness.
Yeah, that was actually a big part of the problem, and that's more of a problem, that's error between keyboard and monitor, but still, man. I mean, it's hard to keep track of that shit in your brain.
That's why I say floating point. The floating point version of SSC is so much simpler.
Oh, of course, yeah. That's definitely easy mode.
Yeah.
And yeah, like
my training wheels.
I mentioned it before, but I don't know. I wanted to do the integer version because that information is not on the internet. You can hardly find any information on that. So it's like it's like a lost art, right? So it's the thing I wanted to teach, but then again, starting off from there is like you probably want to get your SIMD simple concepts down before you try to do all that shuffling bullshit and weird bit manipulation tricks.
So I guess the main use for the integer SIMD would be video encode decode.
Yeah, I see it mostly as video encoding, decoding, and filters is where I see the most use of it. But I mean, you can use it like, remember I put it to use to make a the Game of Life, Conway's Game of Life simulation thing. So it can be used in a lot of different ways, or just basically crunching integer numbers if you have a lot of them to crunch, just like with floating point SIMD. But yeah, I don't know. It's generally you get the bigger speed up from floating point because floating point is inherently a much slower than integer operations, so it's more commonly becomes the bottleneck, I guess.
Yeah.
But anyways, what is done is done. It is interesting stuff to learn, but it's also hard as fuck. That's what I'm trying to say.
Yes, it is. Especially since there's not like always a one-to-one comparison between the x86 integers and the SSE.
Right.
All right, so Robert says, so question.
All right, I'm all ears. There's no question though. Where's the question though?
He's probably still typing.
He's typing it. I'm an impatient motherfucker here. What can I say?
In a world of instant gratification. Why is the CT from the D toggle at the bottom hooked up to the data in the 3 D toggles at the top?
Why is the count from the toggle at the bottom hooked up to the data on the 3 toggles at the top? Are we talking about the good old... Wait, are we talking about the counter here? Wait, that's not the counter. The counter. This one. D toggle at the bottom hooked up to the data in the D toggle. Okay, so if that's what he's saying, maybe I fucked something. Maybe that's why there's something wrong here. No, it's the top circuit. Wait, do I have a...
Zoom out a little bit.
Okay, yeah, well, let's zoom out. I don't think I have a toggle in here. I've got a counter. Is that what you mean? Is this... Yeah, this is a counter, right? Yeah, it's a counter. 8-bit counter. Are we talking about counter, or are we talking about these D flip-flops here? Registers. These ones here. Yeah, everyone fucks up. I fuck up all the time. About 50% of the words that come out of my mouth aren't what I was actually intending. It's just weird. All right, so why is the CT... well, I mean, these ones don't have counts, right? They have enables. And they have clocks. So I'm guessing you mean the enables?
Yeah, those D flip-flops on the top are connected to the CT on the registers on the bottom.
Okay, well, if that is the case, then I've seriously fucked up. But here.
What about down further to the right?
Yeah, so here they come into here, and then they go down here. But I don't see where they're connected to the CT on the register in the bottom. CT here goes into here, and the enables go into here. So they're not connected. Or, oh, does he think that these are all connected together? Not here, down right next to RAM. Okay. Right next to RAM. Here. Why are the D flip-flops? No. The lag is killing me here. Here, I'm guessing he means this, right? So these aren't all connected together. These are all their own separate lines. They're just bundled together into one circuit here. Nah, not one circuit, but one wire.
No, he is talking about the other one next to the RAM.
Okay, good. I'm glad he knows that. Wow. I don't know what he's talking about.
Yeah, right there.
Right here. Okay. The clock is connected here. Wait, what was the problem?
CT's connected to...
The data? Because the CT only goes into here, right?
Well, it looks like the bottom blue line also.
This is the clock, right? This is the clock. So that's the clock. That's the count. Yeah. Follow that bottom blue line all the way around. So this is the clock. Clock goes all the way around. Oh wait, did I fuck it up?
Yeah.
Here. Oh, okay. I get what you're saying now. Okay. Wait, no. That's fine. This one is clocking all of our memory, right? So it clocks that. It's got to clock these two, which it does. And it goes all the way around here. And it clocks these ones here. Right? Because they need clocks, right? They're flip-flops.
Okay.
They need their
Probably
clocks.
because it's so small that it looks like it's labeled CT. The one that coming down. No, further to the left?
Yep. This? I don't know. I think it's fine though. Yeah, that's clock. This is a clock on the top. These aren't toggles. These are just data flip-flops. So they just take the values in from the status bits out of the ALU. All right, good. We have settled it. Once again, Chile is victorious. Wait, it wasn't a competition? What do you say? I don't acknowledge that. Anyways, thanks Robert for your Yeah, they didn't label it. It's just this is the standard label for a clock, right? This this angle thing here. Yeah, same thing there. Oh, it looks, yeah, I guess you could see it looks like this is the counter because it's so close together, right?
Mm-hmm.
I guess that maybe that was the problem. Yeah, it's really close together. They could have, gave a little more space in this model here. But whatever. They are separate. All right. So good stream, everybody. And I will see you guys probably in 2 weeks, but we'll see.
Sounds good.
All right.